Alright, in this video we're going to take a look at 4 problems to practice quantitative electrolysis and electroplating. So these are using Faraday's laws, current, charge, the Faraday, the fact that 1 mole of electrons carries 96,500 coulombs of charge, etc. As you read the question, you can pause the video, try it yourself, and then see if you've got it right. So the first question says, what mass of lead would be produced at the cathode by the electrolysis of molten lead bromide using a current of 5 amps for 3 hours? Now, just a little bit of review from a qualitative perspective. If you're doing an electrolysis of molten lead bromide, there's only 2 things that are in that dish in the picture. There would be Pb 2 positive, it says lead 2 bromide, so lead 2 positive is floating around in there, and then Br minus is floating around in there. Because it's molten, it's melted, it's in a liquid state, the ions are able to move around. Since there's only 2 things present, the cation, the lead, is going to go to the cathode, it'll be attracted to the negative terminal, and there it's going to be reduced to form lead. The bromide ions would be attracted to the positive electrode because they're negative. They'll go to the anions, go to the anode, and there they will be oxidized and form bromine. So we're interested here in the lead, and we want to know what mass of the lead would be produced. So we're going to answer the question using a string of unit multipliers, but before we do, let's look at the half reaction. The lead 2 positive is going to gain 2 electrons, 2 moles of electrons for every mole of lead 2 positive, and that's going to form a mole of lead metal. So for every 1 mole of lead that forms, 2 moles of electrons would have to be used up. We also see the current, 5 amps, and we know that that current means that there's 5.00 coulombs of charge for every 1 second. The current is how fast the charge is flowing through our system. So now we can jump in with some unit multipliers. We'll start with the time because we don't want to start with the unit multiplier, so we're not going to start with the current. We'll start with the time, 3.00 hours. Now if you know how many seconds are in an hour, then just convert it to seconds with 1 multiplier. If you don't remember that there's 3,600 seconds in an hour, then first convert it to minutes, then convert it to seconds. I'm going to just convert directly from hours to seconds. 1 hour, whoops, just switched pens there. So converting the hours directly to seconds, 1 hour has 3,600 seconds. Now we can get the current into this. The current was 5 amps, so 5 coulombs per second, so we can switch seconds to coulombs. 5.0 coulombs per second was the current. Now I'm going to use the Faraday. The Faraday is the charge carried by a mole of electrons. We can convert the coulombs into moles of electrons, E minus. 1 mole of electrons has a charge of 96,500 coulombs. In our data booklet for grade 12 chemistry, on page 3 at the top, you'll find a table of constants, and the Faraday is listed there. It's in scientific notation with extra significant digits, so it looks something like 9.6495, I think, times 10 to the 4 coulombs per mole. So if you forget the number on a test, remember it's in our data booklet. So now I'm going to look at the half reaction, and in the half reaction 2 moles of electrons will make 1 mole of lead. So we can switch moles of electrons into moles of lead. 1 mole of lead for 2 moles of electrons. And finally, we wanted the mass of lead, so we can get rid of the moles of lead and switch to grams of lead. 1 mole of lead, the molar mass from a periodic table, 207.2 grams. So there's the setup using a string of unit multipliers. Now just pay some attention to significant digits. We have 3 hours times 3,600 times 5, divide by 96,500, divide by 2, and times by 207.2. 57.97 or 58.0 grams of lead will form. Okay, 58.0, 3 significant digits in the final answer. All right, here's a second question. Again, read the problem, pause the video, and try it yourself. So how long will it take to deposit 1 gram of gold metal during the electroplating from a solution of gold nitrate with a current of 10 amps? Can you tell from the formula where we're getting the gold what the charge on the gold is? There's 3 nitrates bonded to it, and we know that nitrates are -1. So that gold that we have in the solution was gold 3 positive. Au 3 positive is the charge on the gold initially. And now we're going to reduce it, so 3 positive is going to gain 3 electrons, and it's going to form gold metal. Our current is 10 amps, so the current means there's 10.0 coulombs for every 1 second. That's what the current means. All right, so now we have 1 gram of gold that we're trying to deposit it, so I guess we'll start with that. Again, we don't start with the with the unit multiplier, so I'm not going to start with the current. I'm going to start, in this case, with the mass of gold. So we have 1.00 grams of gold that we're trying to produce. We'll switch from grams to moles of gold, and then using the using the half reaction, we can go from moles of gold to moles of electrons. Using the Faraday, we know that a mole of electrons has 96,500 coulombs of charge, so we can go from moles of electrons to coulombs of charge. And finally, using the current, we can go from coulombs to seconds. Now, if we wanted to, we could also go from seconds to minutes, or minutes to hours, etc. The first unit multiplier is the molar mass of gold. 1 mole of gold weighs 197 grams. That's got 3 sig figs, so I don't need to include any decimal places. That's pretty good. The half reaction, 3 moles of electrons will produce 1 mole of gold. The Faraday, 1 mole of electrons, carries 96,500 coulombs of charge. The current was 10.0 coulombs per second, and 1 minute has 60 seconds. So that should do it. So we'll take 1, divide by 197, times by 3, times by 96,500, divide by 10, and divide by 60. I get 2.45 minutes. Now the question didn't say how many minutes, it just said how long. So if you wanted to leave your answer in seconds, that would be perfectly acceptable. You'd get 147 seconds if you were to not include the last unit multiplier there. All right, the third question. This one, now the first question we asked, how much product could we make in a certain period of time? The second question we asked, how long would it take to deposit a certain amount of product? This third question is asking, what current do we need? So this is the third type of problem that we could ask. What current do we need to plate 0.5 grams of silver metal on the surface of a spoon in 30 minutes? Now remember, when you're doing electroplating, like you see in the picture, the object that you're trying to plate, in this case a spoon, has to be connected to the negative terminal of the battery so that electrons flow out of that terminal of the battery into your spoon, giving the spoon a negative charge, and now the spoon will attract the silver cations, so the spoon is going to become your cathode. So remember always to have the object that you're trying to plate, it must be the cathode in your cell. The other electrode here, the anode, is a silver strip simply to replace the silver ions that are being reduced at the cathode. So every time a silver ion is reduced on the surface of the spoon, a silver ion is going into the solution from the silver strip. So the concentration of silver in the solution stays constant. But of course, eventually the silver strip will dissolve and you'll need to replace the silver strip. So let's jump in. Do we start with the grams or do we start with the time? The key would be to think about, I guess, a couple of ways you could do this. One would be to think about what current is. We're trying to find current. Current is charge divided by time. So if you understand that, then you realize we're not going to start with the time. Instead, we're going to go find how much charge flows through, and then at the end, we'll divide that by time. Charge divided by time is current. Another way to look at it would be, if we start with the 30 minutes, well, what could we do with that? Well, we could possibly convert it to seconds, but then we wouldn't be able to go anywhere else because we don't know the current, so we couldn't go anywhere. But if we start with grams of silver, we could switch to moles of silver, moles of electrons. We actually have a path to take. So there's the clue. Now the half reaction here, the silver is silver positive, so Ag positive. You can see that in the picture. That's the only common charge for silver cations. It's going to be reduced, gaining an electron, to make silver metal. So 1 mole of electrons produces 1 mole of silver. So let's start with the 0.500 grams of silver. We'll get rid of grams, switch to moles of silver. We'll get rid of the moles of silver, and we'll switch to moles of electrons with the half reaction. Then we'll get rid of moles of electrons, and using the Faraday, we can switch to coulombs of charge. Now we've arrived at charge, coulombs. Now remember that current, the thing we're trying to find, is charge divided by time. So we're not going to we don't want to get rid of coulombs now. We've got coulombs, which is good. We want to end up with coulombs per second. That's what current would be. So to get the per second, we have to divide the charge by the time. So I'm just going to put a 1 on top of the next multiplier. And the time here was 30 minutes. Now you could go off to the side and convert that to seconds and just put it in here. Or you could just say to yourself, I've got the charge, I'll divide by the time. And the time here is in minutes. And then with one more multiplier, convert those minutes to seconds. Because the minutes were in the denominator, we put them in the numerator of the next multiplier to cancel them out. So the first multiplier is the molar mass of silver. 1 mole weighs 107, whoops, I just erased again. Times, boom, 1 mole of silver is 107.87 grams, periodic table molar mass. From the half reaction, 1 mole of electrons will produce 1 mole of silver. The Faraday, a mole of electrons has 96,500 coulombs of charge, and now dividing by the time, we had 30.0 minutes, and we know that 1 minute has 60 seconds. Now if you cancel out everything, the grams will cancel, the moles of silver will cancel, the moles of electrons cancels, and the minutes cancels. The only thing we have left are coulombs per second, which is the same thing as amps. So we know we've set this up correctly. So grabbing a calculator, 0.5 grams of silver, divide by 107.87. The ones we can ignore, so times 96,500, divide by 30, and divide by 60. We end up with 0.248 amps. Now, if you left it as 0.248 coulombs per second, that would be fine. But normally we would say coulombs per second is amps. All right, the last question. Again, try to pause the video and try it yourself. The student's going to perform the electrolysis of an aqueous solution of copper to chloride. A gas is observed at the anode. Which gas would it be? Well, this is an aqueous solution. So unlike the first example that we saw in this video, which was molten salt, this is an aqueous solution. So there's three things in the beaker. There are copper cations, Cu2 positive. There's chloride anions, Cl minus. And then there's also lots and lots of water, H2O. Now the problem is the cathode, so the negative terminal of the battery, is sending electrons like this into our cell. So this will become a negatively charged rod or electrode. That negatively charged rod is going to attract two things. The obvious thing is it'll attract copper, but it's also going to attract water. Remember that water is polar. It has a positive and a negative side. So the positive side of the water, the hydrogens, will be attracted to that electrode. If you have a data booklet, you can look up in the booklet the reduction potential for water. You'll see that it's, if I recall, it's negative 1.23 volts, I think. And then the reduction potential of copper, its reduction potential is positive 0.34 volts. So copper has the higher reduction potential, so on that electrode, water's not going to be reduced, copper will be. And in the picture you can see some reddish-brown precipitate. At the other electrode, the positive electrode, because the electrons are leaving from there and going back to the battery, so that electrode becomes positively charged. It's the anode because it attracts the anions, Cl minus, and of course, because water has a positive and negative side, it attracts water molecules. So now water could be oxidized or chloride could be oxidized. Now if you were to look it up on a data booklet, you would see that water's oxidation potential is larger than chloride. Not by a lot, but it is larger. So using the logic that we've been using, you'd be led to conclude that water would be oxidized. And the product of water's oxidation is oxygen gas. However, this is the one exception to that we need to know. Chloride ions, even though they have a lower oxidation potential than water, they tend to be oxidized instead of water. So chloride ions will be oxidized to chlorine gas. Cl minus will be oxidized to chlorine gas. The explanation for this is not straightforward. It's something to do with something called an overpotential. And my understanding of that is that it's the potential needed to start the process. It's lower for chloride than it is for water. So even though chloride has a slightly lower potential, it has a lower overpotential, the potential needed to start its oxidation. So therefore chloride ends up being oxidized instead of water. So chloride becomes chlorine and loses 2 electrons. That's the only exception that I would expect you to know for that basic process. What we always do is look at the two things, water and the ion, and we ask which one has the higher reduction potential. At the cathode it was copper, so copper gets reduced. Normally at the anode we do the same thing and say whichever one has the higher oxidation potential, that's the one that would be oxidized. And this is the one exception to that. All right, so what volume of this gas, of the chlorine gas, will be produced if a current of 12 amps is used for 60 minutes? We're going to need to do two things for this, and I'm going to do one right above the question and one right below. What we'll do first is a string of unit multipliers like we've done earlier. We'll take the 90 minutes, that's our starting point, and see if you can set up some unit multipliers to go find the moles of chlorine gas, the moles of Cl2 that will be produced. Right, switch your minutes to seconds, switch your seconds to coulombs, switch your coulombs to moles of electrons, and switch your moles of electrons to moles of Cl2. So now the first multiplier, 60 seconds in a minute. The second one is our current. The current was 12 amps, so 12.0 coulombs per second. The third comes from the Faraday. 1 mole of electrons is 96,500 coulombs of charge. And the third is the half reaction, which I wrote above. 1 mole of Cl2 gas came with 2 moles of electrons. So grabbing a calculator, we can evaluate how many moles of chlorine gas would be produced. And I just realized there's missing information in the question to answer the next part, but let's jump in. So you have 90 minutes times 60 times 12, divide by 96,500, divide by 2.336 moles of chlorine. Moles of Cl2. Now the question part B says what volume of the gas would be produced, and I just realized the question doesn't tell us the temperature or the pressure. So I'm going to add this in. So let's say at 20 degrees Celsius, and let's say a pressure of 100 kilopascals. All right, so pause the video now and see if you can do that. If we know how many moles of chlorine, what volume would be produced? If you're thinking, well, that's grade 11, grade 11 chemistry, the ideal gas law, then you're on the right track. Remember that PV was equal to nRT. So rearranging the ideal gas law, V, volume, is nRT divided by P. N is the moles of gas, so 0.336 moles of chlorine gas. R is the ideal gas constant, and its value depends on the pressure units. This is grade 11 chemistry. If we're going to use kilopascals for pressure, then the value for R is 8.314. If we were using atmospheres for pressure, then R is 0.0821. Temperature has to be converted from Celsius to Kelvin, and to convert Celsius to Kelvin, you add 273. So 20 degrees is going to be 293 Kelvin. Finally, divide by the pressure in kilopascals, 100 kPa. When you find volume with the ideal gas law, the units for volume are always liters. So 0.336 times 8.314 times 293 and divide by 100. So 8.18 liters of Cl2 will be produced if it's measured at 20 degrees Celsius and 100 kPa. The first part of this question is electrochemistry, so feel good if you've got that. The second part is just a review back to grade 11 chemistry. Don't worry about if you got hung up on the ideal gas law. So there's 4 questions reviewing electrochemistry, electroplating, and electrolysis questions from a quantitative perspective using calculations.